We would like to take a moment to recognize the understated potential of compressed air, and we would like to focus on its evolution related to clean energy. In the Recovery 2.0 process, one of the 4 primary working fluid arteries is the compressed air pipeline. The Recovery 2.0 system is an innovative approach to manage the treatment of residual waste materials, in a sustainable method by treating waste as a resource, while assisting with the world's demand for clean water and clean energy by using thermal reduction. Within the Recovery 2.0 process, we have focused a great deal of effort on energy recovery in an effort to manage the energy continuum, while attempting to maintain a balance or equilibrium with our environment. We believe that the versatility of compressed air is highly underrated. From the traditional use of pneumatic power, and as an energy storage medium, evolving to thermal energy applications. Compressed air is a symbiotic working fluid, especially in combination with other materials such as water. Air compression is a highly robust process that lends itself to rapid short-cycle regeneration. Pneumatic power. The traditional use of compressed air pneumatic power is as a force to drive mechanical devices such as actuators, air engines, valves and switches, and air jet separation systems. Within the Recovery 2.0 system, we also extensively make use of compressed air starter motors, to overcome the inertia to rapidly generate motion from a standing start. This proves invaluable in maintaining flexibility with intermittent, stop and start processes. Automated starter motors are most effective in applications such as Stirling engines, low-speed wind turbines and gravity-assisted devices and cycles. Compressed air may be used as a booster to drive an over-centering force, that is required to perpetuate motion cycles, by providing a spurt of air at an ideal pulse time, so that momentum may be maintained. The legacy linear thinking of compressed air systems are typically related to the operation of compressors, without any attempt to harnessing the vast amounts of heat generated in the compression stage. Historically, pneumatic power has been thought of as a single-use process, where the air is expelled into the ambient environment and lost. Applying a more advanced, circular strategy, towards a compressed air cycle, you may be able to take advantage of not only pneumatic pressure, but in addition, exploit the thermal properties of air. Let's begin by taking a look at the air intake system. Ambient air may be drawn in and funneled down a wind tunnel into the air preparation stage. This may be co-located with a direct air capture, DAC system, that absorbs dilute CO2 from ambient air. Both the compressed air system and the DAC system require an input supply of clean dry air. This may be achieved in the preparation stage by filtering particulate from the incoming air flow and dehydrating the air to remove excess moisture or water vapor. The clean dry air, which is now also CO2 reduced, may now enter the compressor, where the compressor motor can do its thing to pressurize the air. During the compression process, both the compressor motor and the compressed air itself generate a large volume of heat. This contained heat may be extracted with a heat exchange setup. This heat may be directed into a thermal storage bank or may be converted into another form of energy. After the heat exchange step, the resulting compressed air is cooled and will eventually reach ambient temperature. The compressed air is stored in pressure vessels, cylinders or tanks, for release on demand as required. Multiple storage tanks may act as an energy storage battery, which may be ideal to store intermittent energy sources such as solar or wind. Within the Recovery 2.0 system, one of our preferred uses of compressed air is as a cold side heat sink. The rapid expansion of the release of on-demand compressed air is ideal to be used in steam condensing engines. The rapid expansion of compressed air creates artificial wind on demand. The artificial wind may be harvested with a turbo machine or a turbine. Rapid expansion of compressed air may also be converted in a twin-screw compressor generator. The generation of electricity from compressed air may be achieved in a pumped heat energy system by harnessing the compression and expansion cycle. A common Brayton cycle may drive a heat engine to create the rotary motion to generate electricity. The accumulation of process-contained pipeline air, expelled into a bio-lung as a buffer storage well, provides access to a reservoir of clean dry air, that is ideal for short-cycle regeneration. Air is a particularly robust working fluid that may be regenerated almost infinitely. The potential for the symbiotic uses of compressed air, in conjunction with other working fluids such as water, we see devices such as pressurized hydro storage or hydro accumulator towers and liquid piston Stirling engines. When we finally decide that we are done working a volume of air, we need to manage the exhausted and waste air flow. One method of dealing with the clean exhaust is by routing through a solar chimney, where we get an opportunity for energy harvesting with an airflow turbine. Another option is by venting the exhaust through a piezoelectric grate. We intend to discuss additional aspects of the energy and resource recovery sector at some point in the future. Until then, please feel free to contact us at your convenience. Recovery 2.0 is a project developed by Waste.net, in an effort to reinforce our belief that as rational human beings, we must accept the ultimate responsibility to leave future generations with a safe and sound environment, and a world that has not been depleted of its resources. Please feel free to visit us today at www.waste.net.